Good afternoon, everybody. Welcome back. Today, we're going to talk about the 2023 January USACO Platinum problem number 1, tracker pass. This problem is like this. So you have trackers which has an inclusive interval left eye, right eye. And note that all the left edge is continuously increase, on the right edge, a continuous increase. Right? This is one of the standard problem. There's no two intervals that one will completely overlap the other. So then two trackers adjacent if they basically intersect. Then if two trackers are adjacent, then you can go from one tracker to another tracker. Right? So there is a path that you can go from the first tractor to the end, the last tractor. Then there's a minimum jump. You can go from one tractor to another tractor. The minimum pass, the shortest pass is the minimum number of tractors. So the question they're asking for you is if they give you that, so for example, in this case, right, tractor 1 is from here to here, 2 is from here to here, right? So if they give you an interval, starting point and end point, from one tractor to another tractor, what is the shortest path? Meaning the minimum jump. Right? The second question is, if some of the tractors are special tractors, how many of those special tractors will be at least in one of the shortest paths? Okay, so the tractor are like this, right? So for example, you have one of them, let's say it's L1 and R1, right? You have a second one, L2, R2. Then you can jump from here to here, right? Then if you have the third one, let's say it's L3, R3, right? You can continue jump. Then if you have the other one, L4, R4, then they're not overlapping, you can jump. How to solve this problem? Let's say if you want to go from tracker A to tracker B, okay? That I'll just use a single point to represent each tracker. So you can see this tracker can go from here to here to here, right? From 1 to 3. So if you can find this tracker, let's say, if you can find, let's call it neighborhood A1. Let's say the furthest tracker you can go, okay, and still connected. Let's say you go to A2, okay. From A2, let's say the furthest you can go is A3. You continue go like that until you get to the point of, let's say, A of K, okay. Then this A of K, it's a track, right? This A of K is B or past B. Then I would claim this is the shortest path. The reason is that if it's not the shortest path, let's say you can get at a point here, okay? Let's say you jump from here to this tracker and from here to there. But this tracker can be reached by A2, right? And A2 can go all the way to A3. So why you waste two jumps that you can do for one jump? So obviously, so this is the shortest path. If you can do the same from B, you reverse jump it. B go to B1, B1 go to B2, and then you go all the way to B of, let's say, K prime. So for the same reason, this is also the shortest path. So that means this k and this k prime should be the same, right? So k prime equal to k. And that is your number of shortest paths. Right? So that solves the problem of if you can figure out all those, right, then you can count how many are they, what's the k, then that gives you the number of shortest paths. And then what about how many special track here? So if you take this interval bk prime, which is bk, to ak, take this interval. Obviously, ak is bigger than or equal bk, right? And count number of special trackers inside it. Then that is the answer. Because, as we just pointed out, if there's a tracker here, right, it is in the short, it is, there is a shortest path to make you there. Or even if it's here, right, because obviously you can go from here and reach that, right? So that means this is one of the shortest paths. So now that's the solution. Now we look at the complexity, what do we need? So n is 2e5, right? So we need n of log n, right? Obviously, even though it gives you 4 seconds. So how many tasks we need? So the first problem we need to solve is how do we figure out, if it's starting from A1, what is the longest, what is the furthest tracker I can reach? Right? That's one problem I need to solve. The second problem I need to solve is how many jumps, right? What is this K? Obviously, I cannot count, from 1 to 1, right? Even if I have this, if I count from 1 to 1, that's going to be, each one will be On, and now n of them going to be On squared. So this one has to be log n, right? So then the third step is between PK and AK, how many ones, special things I have. Those are the 3 tasks. Okay, let's try to solve this 3 tasks one by one. Yeah. The first task is actually pretty straightforward. As I drew here, right? So there's a reason they say L1 is less equal to L2, less equal to Ln, and the right is like that. So that means you don't have something like this, right? Because if you have something like this is the right of this is less than that. So those things doesn't happen. The reason they sorted it like this, if you took some of the previous problem, you remember this can be easily done in O of log 1 by a double index, right? So meaning you have an index at the beginning, an index at the end, then you move this index down to the last tracker that is still connected, right? For example, this is connected to this, so I'm going to move down. This is the next one is still connected, I move down. This one is not connected, so I'm not moving down now. So I find this is my A2, right? If this is my A1, this is my A2. Once you find this, then you move this first index right down here. You're trying to find what's the most adjacent one from here going down, right? Because everything up to here is still connected to this. So this index will be at least this far, right? So two index keep going, right? So this can be done. So since it's two index, so this is one time, right? O of n, right? You do the same for A and you do the reverse for B, right? So this is O of n. Okay, that's easy. So second is how to count how many. Now I know each of this jump now. How can I count how many jump will get me to B? Okay, I want to do this in O log n. Okay, this is, if you remember, this is the binary jump problem, right? So we learned that when we do LCA, you remember? Okay, so let's go back to the USACO guide. In USACO guide, in the Platinum level, right? We talked about binary jumping. Okay, so that was, remember, that was an issue for us. That's a problem for us to solve LCA, right? In log n time. So it is like this, right? Remember, we had a tree like this, right? So for example, what is the LCA for this point to this point? You can go up, but that is n, right? O of n. You want to be able to find it in n log n. The 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 way to do binary jump, remind you, the way to do binary jump is at each point you find, what how many what's the point you take to do 2 of power of 0, which is one jump. How many is to do power of 1, right? Sorry, power of 1, which is 2 jump. How many is to do power of 2, which is a 4 jump? How many is to do, all the way to power of 2 to the power of 19, right? Because the limitation of n, right? 19 or 20, just to be safe, 21. So once you have this, those are, then every time you do binary, right? You cut it by half. For example, your search is 2 to the power of 10 jump crossed over B. If yes, I cut in half is 2 to the power of 5. Yes or no, then go here, go here, right? So we take a binary jump, then jump in, that allow us to find the K, right? In O n log n time. Okay. So then the third step is by doing, you do it for A, you do it reverse for B, right? Then you get BK and AK. So the question is, between BK and AK, how many the ones and the zeros? That's a simple pre-sum issue, right? Very simple pre-sum problem. And that is O of 1. Right? So by doing those 3 steps, so you have, this is only doing to figure out all those A's and all those B's, right? So that is over one time. Then for each query, you do a log n, right? You of course have to pre-calculate, right? All those 2 to the powers. Then once you have that, then the search is log n. Then to calculate the how many special trackers is O of 1. So in total, then you have O of n log n, right? Pretty straightforward. So to summarize, you basically do, you can call this greedy or it's 1D dice jump, right? It's a sensing. So you do this. That is your approach, right? Find A and find B. And then the only tricky thing is how do I do this in logger by using binary jump? Okay. Same way we did it when we do LCA. Okay. So if you forgot this, go back to Benjamin Chi's USACO guide and look at the Platon level binary jump. Okay, that's a problem for today. Problem number one, tractor pass. Then next week we will talk about manner corrections. It's another interesting problem. So have fun tomorrow to watch the Super Bowl, and we will see you next week.